In our first lesson of stoichiometry, we'll investigate the terminology of stoichiometry and gravimetric stoichiometry, and we'll learn the process to solving basic stoichiometric problems. Stoichiometry is the study of relationships between the quantities of reactants and products involved in chemical reactions. The word stoichiometry is derived from two Greek words, stoichon, which means element, and metron, which means measurement. So it deals with calculations involving the masses or volumes of the reactants and products involved in a chemical reaction. When we use the word gravimetric in front of stoichiometry, we're referring specifically to the use of mole ratios to predict the masses of the reactants and products in a particular chemical reaction. What we're going to be doing is learning the process of solving mass-mass problems or mass-mass relationships. The type of problem that we'll be solving is one where we want to know how much reactant we need for a particular reaction or how much product we can produce in a particular reaction. In order to make these predictions, there are two main steps. The first step is to start with the balanced chemical equation. The reason we need to start with a balanced chemical equation is because it provides us with the ratio of the substances in the balanced reaction. For example, if we look at this reaction of magnesium reacting with oxygen to produce magnesium oxide. You know that you balance the reaction in order to observe the law of conservation of mass. But if we look deeper at what the ratios actually mean, we can see that what we're being told here is that this reaction consists of two atoms of magnesium reacting with one molecule of oxygen to produce two formula units of magnesium oxide. So the coefficients are helping to give us the ratio of the reactants and products to one another in the chemical reaction, making a chemical reaction essentially like a recipe for a particular reaction. Now, because we deal with larger quantities and we wouldn't be dealing with something like 2 atoms of magnesium, we're going to use the unit mole. So what this means is that for every 2 moles of magnesium atoms, we require 1 mole of oxygen molecules to produce 2 moles of magnesium oxide formula units. Now we need to be careful. This is not a mass ratio, so this does not mean that 2 grams of magnesium reacts with 1 gram of oxygen to produce 2 grams of magnesium oxide. And we know that from our understanding of moles from our previous studies. Now, understanding that the balanced chemical equation gives us the ratio is the critical point to solving a stoichiometric problem. When we want to solve a stoichiometric problem, a typical example is one where we're given the mass of one substance and we're being asked to find the mass of something else in that chemical reaction. And the process we follow is to find the moles of the compound that we're given first, and then we're going to use the ratio from the balanced chemical equation in order to find the moles of our unknown, and then we're going to be able to find out the mass of our unknown substance B. Now you'll notice there isn't a direct relationship between the mass of one substance and the mass of another substance. The ratio exists in the unit of moles. So that's why we need to convert to moles first, then apply the ratio, and then we can find the unknown mass. So let's look at an example where we just study the mole ratio and how to apply it. We have a scenario where we have ammonia and oxygen reacting. So ammonia is NH3 and we're going to react that with oxygen. And we're told that nitrogen dioxide and gaseous water are produced. Now this is our skeleton equation, but we need to balance this in order to proceed. And balancing this is a bit tricky, but if you take a moment by trial and error, you'll find that this is the ratio. Okay, so for every 4 moles of ammonia, we require 7 moles of oxygen to produce 4 moles of nitrogen dioxide and 6 moles of water. In part A, we're asked how many moles of oxygen gas, so I want to know how many moles of oxygen are needed to burn 1.22 moles of ammonia. So I know how much ammonia I have, and I want to know how much oxygen I need in order to consume all of that ammonia. The big idea here is that as soon as you know the moles of one substance in the balanced chemical equation, you can determine the moles of anything else. You can determine the moles of another reactant that's required, or you can determine the mole of a product that can be produced. Much like you can base a recipe on one particular substance. If I have a recipe that requires 1 cup of flour and half a cup of sugar and a quarter of a cup of butter, I can base my recipe on any one of the substances. I can start with how much flour I have. I can start with how much sugar I have. Okay? Or I could even start with how much product I want to make, for example. So in this case here, I know about the ammonia and I want to know about the oxygen. And what we have from the balanced chemical equation is the known ratio. So for every 4 moles of ammonia, we require 7 moles of oxygen. So this is our known ratio, and so what we're going to do is set up a proportion. Much like you would in math, I know one ratio, and I'm going to solve for my unknown of oxygen. So for every 4 moles of ammonia, I require 7 moles of oxygen. Therefore, if I have 1.22 moles of ammonia, I will have X moles of oxygen. And in order to solve for X, I'm going to cross multiply. So I have 4X is equal to 7 times 1.22. And I will solve for X by dividing by 4, and I am left with 2.14 moles of oxygen. So therefore, I will need 2.14 moles of oxygen to react with 1.22 moles of ammonia. In part B, I'm asked for how many moles of nitrogen dioxide and water are produced. So I'll do these one at a time. And the bottom line is that as soon as I know one, I can use it to figure out any other one. Okay? And I can relate any one substance to another substance. Because I'm given NH3, I'm going to base everything else off of NH3. So for nitrogen dioxide, the ratio is 4 to 4, which is really a 1-to-1 ratio. Okay, so I don't need to do any work here. I know the moles of NO2 that will be produced is going to be the same as the moles of NH3 that are used because the ratio is 1-to-1. To determine the water, I know that for every 4 moles of NH3, I will produce 6 moles of H2O. Therefore, for 1.22 moles of NH3, I will produce X moles of H2O. When you're setting up your proportion, you want to be very careful and make sure that your moles match each other. So this is NH3 and this is NH3. This is water and this is water. So sometimes people put the X first because they know that it's what they are looking for. So this is 4x is equal to 6 times 1.22. And when I solve, I find that x is equal to 1.83 moles of H2O. And it's very important to keep track of what you're solving for, in this case x. Now what we've been doing in these examples is we've been starting with the moles of one substance, and we've been using the mole ratio to find the moles of something else in the balanced chemical equation. So this is generally going to be step 2 in a 3-step problem that we'll perform. So let's look at another typical problem, and this is a full mass problem. So I've got iron 3 oxide is mixed with carbon monoxide to produce iron metal and carbon dioxide gas. What mass of iron 3 oxide is required to produce 100 grams of iron? So, as you know, we need to start with the balanced chemical equation. So we start with the formula for iron 3 oxide. We're going to react that with carbon monoxide, which is CO. And we're going to produce iron metal, which is Fe, and carbon dioxide gas. And this is another tricky one to balance. You need 3 in front of the carbon, 3 in front of the carbon dioxide, and a 2 in front of the iron. So in this case, you're given that you have 100 grams of iron. And I find it helpful to extract the information from the problem and write it right below the balanced chemical equation. And what I'm trying to find is the mass of the iron oxide. So in our previous example, we were given information about a reactant, and we were being asked about other reactants or the products. But as you'll see here, we can start with anything. So we can start with the product. We know how much product we want, and we want to work backwards to see how much reactant we're going to require in order to produce that. So we have the mass of iron, which is our compound A in this case, and we want to know the mass of the iron 3 oxide, which is our B in this case. So the process we're going to follow is to find the moles, use the ratio, then find the mass. So step 1, we need to find the moles of iron, and the mass of the iron that we're dealing with is 100 grams, and the molar mass is 55.85. Now you want to be very careful here. What you're going to see is that when I find molar masses in stoichiometric problems, I only use the formula. I don't apply the coefficient when I'm finding the molar mass. The coefficients are applied in our ratio step. And so when you're finding your molar mass, you don't want to use the coefficient, otherwise you'll end up using the coefficient twice in the problem, which is not what you want to do. So in this case here, I have 1.7905 moles of iron. And sometimes if you put moles of iron there, it's easier to keep track. So this is our moles of iron. So we've accomplished step 1. Step 2 is to apply the ratio. The ratio here, for every 2 moles of iron, there is 1 mole of the iron oxide. I'm looking for the iron oxide. Okay, so it's a 2-to-1 ratio, so I'm going to require half the amount. of iron oxide. So this is the moles of iron oxide that I need for the reaction. So I've gotten to this step here. So my last step is to find the mass of iron oxide. And mass is equal to moles times molar mass. The molar mass of iron oxide, I take twice the molar mass of iron plus 3 times the molar mass of oxygen. And remember that when you are finding your molar masses, you're going to use 2 decimal places in order to keep a lot of significant digits. And what we find, we get 142.97 grams, which we're going to round to 4 significant digits because that's what we started with at the beginning. So that's going to round to 143.0 grams. Okay, so the amount of iron oxide that I need in order to produce the appropriate amount of iron is 143 grams. Okay, we'll do one more example together and then you can try one on your own. So what is the mass of sodium that could be produced by the decomposition of 250 grams of sodium chloride? So we've got sodium chloride, the decomposition reaction, we produce sodium and chlorine. Okay, this is one of the reactions we learned earlier in the year. Decomposition of an ionic compound into its elements. So when we balance this, we've got a 2 in front of the Na and a 2 in front of the NaCl. In this case, we're starting with 250 grams of sodium chloride, and we want to know how much sodium can be produced. So this is our A, and this is our B. Step 1 is to find the moles of the sodium chloride, which we're going to do by taking the mass and we're going to divide by the molar mass, which in this case is 58.44 units of molar mass being grams per mole. You'll notice again that I didn't apply the 2. It's the sodium plus the chlorine, which gives me the 58.44. This gives me 4.28 moles of sodium chloride. Step 2 is to apply the ratio. In this case, the ratio is 2 to 2, which is 1 to 1. Therefore, the moles of sodium is equal to 4.28. And step 3 is to find the mass of sodium, which we do by multiplying the moles that I have by the molar mass. And it's the moles of sodium, which is 4.28, times the molar mass of sodium, which is 22.99. Okay, and that gives me 98 grams, which is properly reported to 2 significant digits. Okay, so I'd like you to try example 4. It's asking you to determine the mass of carbon dioxide when 12.5 grams of ethane reacts with excess oxygen. So when it tells you that it has excess oxygen, you don't need to worry. Okay, the mass that you should obtain is 36.6 grams. So I'd like you to try that on your own and verify your answer.